Right. Okay. Anything else? Okay. Good. So.
Perfect. Thank you. So, I think the title of my lectures on the website was something like numerical methods for topological phases or whatever. Actually, I will be more accurate about the title. I will talk about entanglement spectroscopy, so entanglement spectrum, and mostly how do you apply this technique to topological phases. So one thing I didn't say yesterday is, well, I'm doing numerics, right? So it's close to be an experimentalist, actually. So my point of view will be the one of someone doing like codes and looking at data. But one thing I won't do during these lectures is to give you like technical details about how to write a code to do the entanglement spectrum and all that kind of stuff. But please, if you have any questions about how to do that with your computer, just ask me. Pay me a coffee or a beer. I will be happy to help you to write your code. It's free? Damn! Not the beers. Okay, good. So the motivation behind this the story of entanglement spectrum can be the following. Let's say you do some numerical simulation. Your PhD advisor, your postdoc advisor asks you to, okay, look at this microscopic model and tell me if there is any emergent topological phase there. So there are two things that you want to do. Well, the first thing is you want to convince yourself. It might sound stupid, but when you do numerical simulation, you do that for a small number of particles or a small number of sites. And somehow you want to be sure that what you're looking at is actually really, well, the phase you are interested in. So the more evidence you have, the better it is to claim that, oh, I have strong evidence that this phase should emerge in that microscopic model. So definitely this entanglement spectroscopy will be one more tool to convince yourself. The second thing is you want to minimize your effort. In a sense, if you have Hamiltonian for your microscopic model, the simplest thing that you can do basically is to compute the ground state, is to obtain the ground state. Whether the method you use, you can use exact diagonalization or you can use de-energy. But at the very end, the simplest thing that you can get is the ground state. So you would like to get as much information as possible from this ground state. And actually, so the reason why you're limited to the ground state, it's not because you're lazy. It's because basically, if you want to compute excitation or to have like a larger part of the spectrum of your Hamiltonian, it's quite difficult. Be it, once again, exact diagonalization or other techniques. So if you can get everything from the ground state, that would be great. Like, can we probe the excitation from the ground state? And this is one of the things we will see with the story of the entanglement spectrum. Remember that we will deal with many quantum systems. So the effort that you have to do in terms of calculation is exponential. It's exponential with the system size. Think about like spin 1/2, the spin 1/2 system. You know that the Hilbert space will grow like 2 to the power the number of spins. So adding one more spin is actually quite tricky in many situations. So try to get as much as you can from the ground state and from finite size system. So imagine you have only the ground state. What kind of calculation can you perform to be sure that, well, this is the Laughlin state in this model? Well, if you're lucky, one thing that you can do, you have a model state. And the simplest way you can check, like, imagine once again, this is the Laughlin state, for example, for people that know the Laughlin state. So the simplest thing that you can compute is basically the overlap. which is just the scalar product between the two states. Unfortunately, sometimes it's not that easy to compute even the overlap between two states. The first reason is that, well, if your model state is not, you cannot write it in the same basis that you write your exact state that you have from your numerical calculation. Computing the overlap can be quite painful. And the other reason is at the end of the day, an overlap is just a number between 0 and 1. So you have to decide, is it a good overlap if I have 0.99? This one is fair. You will say, okay, it's really close to the model state. But now imagine you have 0.5 or 0.6 for a very large algebraic space. Is it a good overlap or not? Yeah, it's a bit more difficult to decide. So that's one thing that is doable. Of course, you can imagine that you have some global order parameter. You can, of course, look at the ground state degeneracy. If you can change the genus of the surface you're working on, like you can go from, let's say, the torus or the sphere to the torus, and see all the degeneracy of the ground state changes when you change the genus. That's one way to probe the topological order. You can play with the boundary condition. You can see what happens to your system where if you're on a torus, you twist your one end of the, when you glue you have the cylinder, you glue it back, you can twist it and see what's going on to your system. Or similarly, if you think about the fraction quantum, the quantum Wall effect, you can think about the flux insertion and see how the system react. So that's all. These are different techniques that you can apply to try to see. Yeah.
So what do you mean, like local order parameters, like full large invariant, or?
Yeah, for example, yeah, if doable. Not a local one, since we are interested in topological phases. So that's why, like a few years ago, people have have tried to apply different techniques coming from the quantum information to probe this system, these topological phases. So maybe the most famous one is the entanglement entropy. Okay, so just what is the idea behind the story of the entanglement entropy? So you have your ground state. You can imagine that the system is within the plane, and you will cut your system into two regions, A and B, and you will try to quantify the entanglement within the ground state between the part A and the part B. And as you already may know, by computing the entanglement entropy between the A for the subsystem A, you can get information, you can get characterization of the topological phase you're looking at. So we will discuss this point today in more details. But actually, what happened in 2008 in a paper by Lynn Haldane, instead of looking only at the entanglement entropy, they have decided to look at the full entanglement spectrum. The entanglement spectrum is just the spectrum of the reduced density matrix when you trace out this part B of your system. So when you do that, you get actually lots of information about the excitation of your system. You have all this information only by looking at the ground state. So this is why this technique is quite interesting. Everything you do is to play with the ground state. You break it into pieces, and you look at the entanglement between the different pieces. And you get information about the excitations. Okay, so basically that's the picture I wanted to give about what are the motivations behind using new tools, especially from people doing numerics. So now I will start and give you many definitions that we will need in the rest of these lectures. So about the plan of my lectures, basically today we will discuss the idea of entanglement entropy and topological correction. I will give you the definition of the entanglement spectrum. I will show you the relation between the edge physics and the entanglement spectrum for a simple case. The next lecture will be more about the calculation of the entanglement spectrum for non-interacting system. And now you can see the edge physics emerging from the entanglement spectrum for like a system like the integer quantum Hall effect. The last lecture will be mostly about interacting system, and I think I will focus more specifically on the fractional quantum Hall effect because, well, that's one of the models I know quite well, and because it's also one of the cases where we have lots of studies and lots of results, and it's also a nice model where we can show you that the way you cut your system into two parts gives you different kinds of information. And if I have time at the very end, I might show you how we have used this tool, this entanglement spectroscopy tools, to probe the system like fractional chain insulators, but only if we have time.
One question.
Yep.
You said that looking at the entanglement spectrum, you can get information about the excitation.
Right.
I don't understand, because if you give me just the ground state, this ground state can be the ground state of realization from the time, in principle. So you're looking at the excitations of what?
So basically, the point is the following: you will look at the zero energy excitation of your system, right? So if you think about, let's say you start with the integer quantum Hall effect. So we have a field Landau level. And if you do this kind of calculation, you will get all the excitation which are related to the edge of your system, all the gapless excitation. Right. But your question is perfectly is actually the good question, because I can, as you say, I can always, whatever the ground state, whatever wave function I use, I can always build an Hamiltonian with different kinds of excitation on top of the wave function actually to be the ground state. There is, from that perspective, I don't know what kind of additional condition I have to put on my Hamiltonian to be sure that this will perfectly define the kind of excitation I extract from the ground state. About the locality, for example, of the terms in my Hamiltonian, whether put lots of constraint on the kind of excitation I can get if I require to get that ground state plus locality for the Hamiltonian. But that's the very crucial question of all that story. Okay. So before looking at the entanglement entropy, let me give you a bunch of definitions. So you start with, let's say, a many-body wave function. And I will choose a basis where I can decompose the state. Now, remember that the idea is we want to cut the system into two parts, A and B. So we will assume that you can rewrite any state of your basis as a direct product of two states that's the A part of your system, the B part. You can think about like a 1D system. You can put spin 1/2 if you want. So this basis here will just be like every possible configuration for your spin chain. The part A might be like the 3/1 spin 1/2, and the part B will be the remaining spins. With that picture, you see that you can always decompose your basis on a part that only lives on A and another one that only lives on B.
What about if you have fermions? Because Jürgen said a few things yesterday about fermions, bringing the issue of the kind of difficulty to handle fermions on the same footing as cosmic objects, because the difficulty to find some ordering of the sites and some non-locality. But
here, I don't think for the for the many body bases that you use, you can always, at least for a finite size system, I don't see any trouble to decompose as soon as I fix a given ordering.
But the Hamiltonian, it's not going to be necessarily local.
No, not in that language. Yeah. Okay, so now I can rewrite. So these are the coefficient of my decomposition, and I can always rewrite my wave function as a sum over all the configuration for A and all the configuration for B. B times mu A. Tensor product mu B. Right now I've done nothing, right? I've just used the fact that my basis, I can decompose it onto each state, I can decompose it onto a part of A and B, and rewrite the C lambda coefficient as C mu AB. C mu AB. Okay, so the first definition let me put all the definition I will. We'll need mu A B, C mu A B. So now I can define the entanglement matrix. M. And so the entries of this matrix, so mu A will be the row index, and mu B the column index. And this will be just the coefficient C mu A, mu B. Right. Okay, so the thing I want to reach now is a Schmidt decomposition. So I want to write my state as a Schmidt decomposition. So in order to do that, the easiest way is to use the singular value decomposition. Or SVD. So the SVD allows you to write any matrix. It doesn't have to be a rectangular matrix, square matrix. It can be a rectangular matrix. As a product of a matrix U, D, and V dagger, where D is a diagonal matrix. With only non-negative entries. Right, so I will write D as exponential minus psi1 over 2, exponential minus psi2 over 2, blah, 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 psi n over 2, bunch of zeros.
So they're real?
Yeah, they are real and non-negative, right? It can be 0, but... so the dimension, let's see. So U is a square matrix which has the size, the dimension of the space spread by the state mu A. And it has the following property. So it's not a unitary matrix, but almost. Only U dagger U is equal to 1, which means that the columns of this matrix are orthonormal. Same story. V is a square matrix, which is the dimension of the subspace spread by the mu B, dimension B, and satisfies V dagger. V dagger is equal to 1, which means that the row of this matrix are orthogonal. Right.
What is the guarantee that the diagonal elements are not?
Sorry, just... It's not a square matrix. Yeah. It's much better like this, rectangular matrix. And it has sorry. So the question about non-negative entries. So all these numbers, you can, when you perform the SVD guarantee that the diagonal matrix that you have here, its dimension is actually the minimum of dimension of A and dimension of B. All the entries here are positive numbers. It can be 0 or positive numbers. All right. Okay, once you perform an SVD on the entanglement matrix. Yep.
What's the word between U and matrix?
Rectangular matrix. Yeah, it's not a square matrix. So now once you perform the SVD on the entanglement matrix, what you can rewrite is just state as a sum over I of the entries of the diagonal matrix times a state that lives in A and a state that lives in B. Right? These states We can get them by using the U and V matrices. And they satisfy the following property. They are orthogonal, so Aj is equal to delta Ij, and Bj is equal to delta Ij. Yep. Right now, the only thing I've done is I assume that I can write my many-body basis. I can decompose it onto some part in A and some part in B. Right.
Is there an interpretation of what this orthogonal basis usually is? I mean, is it useful to think of it that way, or is it? It's just that for strongly correlated systems, normally ideal states. It's not just a simple momentum space or real space picture. It needs some combination. It's not as easy to define what is a suitable basis.
I mean, it depends. Just think about spin chain or strongly derived system like a fractional quantum state. I can always use the occupation basis, right? If I think about momentum space, I have a perfectly simple way to define a way to cut my system into two parts. I say that orbitals from 0 to whatever ky equal to that. That's my A part, and this is the remaining part is the B part. I agree with you. It's a bit more tricky if the way you cut your system is not expressed in a simple way in the basis you use to decompose your state. If you think about the relation when you have to. If you use the orbital basis and you want to do the real space cut in your system, this is a bit more tricky, but still doable to do this kind of calculation for a strongly iterative system. At least in finite size.
So what do you need to convert one to the other in that case?
Yeah, you need to find, basically you have to find the overlap between the basis that you use and the basis you want to decompose your state into two parts, A and B.
So does this imply that you need to know some kind of energy identity or some kind of basis for a system first in order to proceed?
My point is the following. Let's say I give you the ground state, or I give you a wave function, and I give you the decomposition of the wave function. It's not trivial to get this decomposition. I don't claim it's trivial. But once I have this decomposition, I can do this kind of cut. Right? Let's say you're using your computer to generate this decomposition. The way you do numerical simulation is always, if you think about the simplest case where you find a size system, like spin 1/2, you have an Hamiltonian which might be quite complicated, but at the very end, when you do the numerical simulation, you have your basis of spin 1/2, and you write all the matrix elements. So you will diagonalize this matrix, and the output of your code will be a vector, which is exactly this series of coefficients C lambda. Right?
Yeah, so sorry, I hope you don't mind saying does this imply that this works the best when you can first perform exact diagonalization on the system?
Well, if you can do geometry, for example, you get it for free. No. You have other works where people have done the calculation using Monte Carlo calculation. Monte Carlo. If you use Monte Carlo calculation, you can also compute the reduced density matrix. I'm not sure that in that case they've computed the entanglement matrix, but you can directly compute the reduced density matrix for your system. Let's say, especially if you have a wave function which is in real space, like expressed with coordinates, and you want to separate your space into 2 part A and B. That's quite difficult, but it's still doable using Monte Carlo in that case. But then you won't use this kind of technique where you go through the decomposition of many-body basis. All right. Well, you can always...
Other than permutation?
No. You can... it's up to... I mean, I can always change the phase, for example. It won't change the normalization of my states. So that's one example of transformation where... Okay, so this is a Schmidt decomposition, so let me add this definition here. Property AI. Aj is equal to Bi. Bj is equal to delta Ij. Right. So now let's say I want to compute the reduced density matrix. So I start with my wave function. I assume that's the ground state of my system. So the density matrix, the full one, is just the projector onto this wave function. And what I will do to compute the reduced density matrix is I will trace out on the degree of freedom that are the part of B. So I can use the Schmidt decomposition actually to get the expression of rho A using these vectors A, I. So as you can see, in this basis, once I've performed the Schmidt decomposition, like here, getting the reduced density matrix by tracing out all the degree of freedom of B, it's quite simple. It's already diagonal on this basis. So I can directly read out the spectrum of the reduced density matrix here. The spectrum of the reduced density matrix is just the exponential minus psi I.
What's the rationale for writing these eigenvalues as exponential? Because one has in mind, of course, the analogy with thermal ensembles, but there's no temperature. You are at 0 temperature. So is there a good rationale for
I can give you like a simple example, a simple idea. If you want to, because you already know the story, so we want to write this reduced density matrix as the exponential of some Hamiltonian minus. So you can claim, well, if I want to make the analogy between the true Hamiltonian of the edge of my system and the reduced density matrix, somehow I want the ground state of the fictitious Hamiltonian, or the ground state of the edge Hamiltonian, to be the ground state of this fictitious Hamiltonian corresponding to the reduced density matrix. So somehow I want the highest weight of the reduced density matrix to be the ground state of the Hamiltonian. So with this relation, you're guaranteed that the highest weight, which is the largest eigenvalue of the reduced density matrix, which will correspond to the ground state of your Hamiltonian. So that's like a simple way to argue why, at this point, we should write the weight.
I guess you're going to spend some time to justify the idea that the probability gap will correspond to some energy gap.
Right.
So that's somehow what is
Right, behind this idea of rewriting the weights in this form.
This is AJI? No.
No. Wait. If you prefer, let's remove, just make a comma and not. Okay. Okay, you can complain about my handwriting. I think it's fair.
May I make a comment related to Benoit's question? What Nicolas is doing is quite general because you can take any wave function. So, for example, suppose you don't take a ground state, but you take a very high excited state. And you can ask the question, can the state be, can a subsystem look as if it's in thermal equilibrium with the rest serving as the whole path? And in that case, these singular values would look like the thermal population, and the subsystem would be like in the canonical ensemble. So that intuition you had, it holds for the high excited states. And then one could even ask if the temperature is the temperature of, because of, that would be a microcanonical, but in a canonical ensemble.
Yes. Okay.
So, just, for people that want to implement this kind of entanglement spectrum story, SVD is really the way to go. Don't diagonalize directly. Don't compute row A brute force and diagonalize it. Do the SVD and get the spectrum this way. It's much better, trust me. In a similar way, you can compute the reduced density matrix for the B part of your system.
Why is using a singular value decomposition more like computationally efficient?
So it's about the accuracy of the eigenvalues that you get. Basically, this one, if you look, you have a square of these guys here. So you lose some accuracy when you do the calculation of the reduced density matrix. Actually, it's quite, trust me, in some cases you want to have very high accuracy on your eigenvalues. So one thing is that row A and row B, they have exactly the same spectrum, right? By same spectrum, I mean that, of course, the dimension of the subspace for A and the dimension of the subspace for B, they don't have to be the same. But now if you look at the non-zero eigenvalues of the reduced density matrix for row A and row B, these two numbers are equal. So more precisely, the statement is that the same number of non-zero eigenvalues. It's quite important. It means that it's useless to compute row B. Once you have row A, you have all the information that you need. And you won't get more information even if row B is bigger than row A. Okay, so that's the Schmidt decomposition, the reduced density matrix. Sum of work psi I, AI, AI.
May I ask a somewhat technical question? So if you're...
Coffee?
Sorry?
You should pay me a coffee first. I'm just kidding.
So if the ground state has some sort of symmetry that is broken by the cut that we make, is that possible? And if yes, how? For example, I can imagine that if I cut a translationally invariant system exactly in the middle, when I break this invariance, I break the symmetry.
Exactly. So
do I need to do this process by breaking explicitly the symmetry from the beginning, like not using the symmetry in the calculation?
No, you can break the symmetry after by the cut.
Okay.
right? You use all the symmetries to get your ground state, because it will be the time-consuming part in your calculation.
Yeah.
But then, once you have this, you can always use a basis. In that case, you have some work to do to go from one basis which has all the symmetry to a basis where the symmetry is not there, because it's easier to cut in this basis where you have explicitly broken the symmetry that was there in the original state, but it's broken by the way you cut your system into two.
Okay. Can I also, for example, write my ground state? Okay, I get the ground state with the symmetries, and then I write it down, I expand it, let's say. Like write it down without the symmetries and then do the whole thing with that.
Yeah.
Okay,
Yeah.
do that.
So actually, the question of symmetries is the next point. So what we will call the entanglement spectrum, it's not exactly the eigenvalues of the reduced density matrix, but minus log of the eigenvalues. So basically, the set of the psi I, that's the entanglement spectrum.
Can I ask you a question?
Yep.
So the choice of the, as you said here in the example of the chain, yours, the sector A and sector B.
Right.
The choice is arbitrary, or there should be a...
It depends how you want to cut your system, how many sites you want to keep for A, right? It's up to you. I mean, you can cut exactly into half of your system, or you can look at one site among the rest of your system, or two. There is no...
So can be, for example, A only one site and B the rest?
Yeah, sure.
And,
You can...
and this condition still holds if that's our choice?
Right. Yeah, you see that the two, directly by this relation, you see that the number of non-zero eigenvalues. Once again, the size of the matrix can be huge. But now you look at how many non-zero eigenvalues you have. This will be the same number that the one for one site. Okay, good. So this is the definition of the entanglement spectrum. All the set of the psi I. And as usual, when you have a spectrum, the thing that you want to have is a way to sort all the numbers. So you want to give them labels. And of course, not just 0, 1, 2, 3, 4, 5. It's a bit dumb. So you want to use quantum numbers to classify them. So let's imagine that you have an operator, O, which commutes with a density matrix. A good example, if psi is an eigenstate of an operator, right, of an Hermitian operator, then you have this property. So it's not difficult to get this one. If you think about the spin chain, the total SZ value, sum over all the SZI, that's one of the operators that will commute with the rho. Of course, if this operator commutes with the Hamiltonian of your system. Good. So now let's assume that O can be written as a sum of an operator that acts only on A, and this part only on B. Once again, think about the total SZ. Sum over SZI, if I take this example here, let's say this will be A, this will be B, A 1, 2, 3, 4, 5, 6. Right, and so the SZA will be just 1 to 2, and SZB will be the sum from 3 to 6.
Question.
Yep.
So, and just about density matrices in general. If an operator commutes with a density matrix, is that like saying that it's an eigenstate of that? You know, if I consider just the psi vector, if it's a pure state, then is that commutation the same as saying that eigenstate is that state is an eigenstate of the operator?
I think so. I have to be really careful, but the other way around, it's for sure. Like if it's an eigenstate, you can definitely show this one. The other one, this one, I think you should prove that it's an eigenstate, because the way you get 0 basically is to show that you will have your O psi is equal to psi O. So I think it's. I will check that and we'll give you the answer. Instead of saying something stupid, let's check that. Okay. But for the timing, imagine like a situation like this one, where you start with an operator which is actually for which your state is an eigenstate. The thing is, you have to be careful because you can generalize this calculation where rho is a sum of projectors, and all these properties will still be true. So what you can show is the following property. Now you want to look at the commutation relation between OA and rho A. So you can do the following calculation. You start from the commutation relation here, and you trace over B rho. So this is just 0 by definition. And now you have the following properties. Let's trace over B of rho A, OA rho plus trace over B of B rho. So this part here is just OA trace B of rho, which is by definition OA rho A.
Excuse me?
Yep.
If the part A interacts with part B, then can you write your operator like that?
Now I assume that I have this operator that I can decompose in this way, right? Once again, if you want to get a better idea of what's going on, just use this example.
Yes, but the problem is we are considering some interacting system, otherwise it will be true.
But you see, I can have an interacting system, but I can still compute the total SZ. Totalization along the Z direction. It's not a problem. Still a sum over the local operator on each side. It's still a many-body problem, right? The wave function here can be really complicated. It can be decomposed into this many-body basis with lots of coefficients you don't know. But still, this operator O that I want to look at has this feature.
But what if the operator was probing a global property of the system?
Sorry?
If the operator is like giving me an indication about the global symmetry of the...
If I cannot write this property, then I will... Yeah. My point here is just to show you that if you have an operator which behaves this way, right, that commute with the density matrix, that can be decomposed into a sum that acts only on A and one acting only on B, then this operator OA commutes with rho A. So you can use it as a way to label all your energy, entanglement spectrum, or all your eigenvalues of a reduced density matrix. Right.
Here, the density matrix you are taking to be the projector of the ground, right?
Mm-hmm.
Is rho that rho?
Right.
Is the projector of the ground.
Right. That was. Right. I start with a single ground state for the time being. Right.
Can you give the physical meaning of this entanglement spectrum?
Right now, I would just try to get. I mean, I need lots of definition. So we'll talk about the physical meaning like in 5 minutes, right?
Are you allowed to cut the system in a funky way? Like in your spin chain, can I consider a cut where I separate it into two bipartite lattices, like 1, 3, 5, and 2, 4, 6? Is that sort of thing allowed?
Right now, I didn't say anything about the specific way. Yeah.
I'm just wondering.
Yeah, you can cut like in with separate intervals, and but
yeah.
let's keep it simple for the time being. So far, so good. Here it's a trace of an operator that acts only on B, right? So this one, when you take the trace of the commutator, it just gives you 0. So what you show here is that if you have this property for the original density matrix and this property for the operator, then you obtain that the operator OA commutes with the reduced density matrix. So it's just, you can use this operator, which you can think like it's a quantum number, to label all your the eigenvalues of your reduced density matrix. So actually, now let me give you one example, like a concrete calculation. So if one was definition, yep. Oh, because it's a commutator, right? And this operator O acts only on B. So you have the permutation. You can permute OB, rho, and rho OB. Okay, so 2 spin 1/2. That's the simplest example that we can imagine. So I take a system where I have a spin, 2 spin 1/2, and I will cut it, of course, this way. So the A part will be the left spin 1/2, and the B part will be the right spin 1/2. And I can take any state and do this kind of calculation. The most generic state has 4 components. And you can, the entanglement matrix for this state will just be this one. So basically here I have the entries for the B part of my system, and here for the A part. Okay, so let's even be more concrete and take just a product state. Up, up. Well, if you write such a state, the entanglement matrix, it's just a 1 at the first entry, first column, and 0 everywhere. So, of course, the Schmidt decomposition for this state is quite trivial. Life is easy in that case. And the entanglement spectrum, well, as I said previously, I can use SZ as SZA plus SZB. This state is an eigenstate of SZ. So I can use this quantum number here to classify the different eigenvalues of the reduced density matrix. And so if I do this calculation, this is SZA, and I will put the 0 here, so this is the psi I. You have only one state, one non-zero eigenvalues in your density matrix. It's the 1. So since we are plotting for the entanglement spectrum minus log of the eigenvalues, you have an eigenvalue, you have a state at 0. For its SZA value is 1/2. And that's it. So that's one example of an entanglement spectrum for the system. Now I can take a maximally integral state. One over square root of 2, spin up, spin down, so a single state. Once again, the entanglement matrix, you read it directly from the wave function. It's a 0, 1 over square root of 2, minus 1 over square root of 2, 0. You can do the SVD for this state. So you can rewrite M2 as 1, just the identity matrix, 1 over square root of 2, 1 over square root of 2, 0, 0, 0, minus 1, 1, 0. And so you can rewrite your state as a Schmidt decomposition. So you have, let me put a plus just to be, remember for Schmidt decomposition, the coefficient that you have in front here has to be positive, right? So this one is not exactly a Schmidt decomposition written this way, because you have a negative sign here. Now I can always define my A and B state in this way. And this one is now a Schmidt decomposition. Of course, it's just a trick. Just move the minus sign from here to just here. But this one, this decomposition satisfies this property here. And of course, I can directly get the entanglement spectrum because I can read out the spectrum of the reduced density matrix. And I will get the following picture. So we got, remember you have to take the square to get the eigenvalue, to get the, when you look at the entanglement spectrum. So you have one state at log 2 for the log psi I, one at minus 1/2, and another one at SZ equal to half. So one thing that you learn here is, in this example, I can look at the entanglement spectrum of these two wave functions, and I can just by counting how many states, how many levels I have in this spectrum here, if this state is entangled or not. This one is not, you have a single value. This one is entangled. You have two values. Of course, this is not what we, well, I don't claim any topological properties here, but just to give you an example where just by counting stuff, you can decide if your system is entangled or not. You can do the same kind of exercise for another state. Let's say this one. You can perform exactly the same kind of calculation, and you will get two states. So one here, one here. Once again, to check that this state is an integer state, you just count. Two levels, entangled. Just one level, not entangled.
Is this equivalent to whether it's a mixed state or pure state? I guess in quantification language they use this thing.
I'm not sure to understand this. So can you just rephrase your question?
Whether or not it's just one state, like a pure state, or whether it's mixed.
Yeah, if it's a pure state, then yeah. Right. Well, you have to be careful. I mean, if you have, depends on how you cut your system. Of course, here there is like not just a one way to cut it. Right? I can always let's say, depending on the way you cut your system, you can get more than one state. Just imagine the integer quantum Hall effect. If you know a little bit the story of entanglement spectrum, remember that the original work by Haldane was using the orbital cut. If you take the integer quantum Hall effect, you get a single state. Of course, it's a product state. Right? If you look, so the entanglement spectrum is just one level. Now, if you cut your system in a different way, like a real space cut, then the number of levels that you will get is not just one. But because you use a cut, basically that is not expressed in a way where your product state can separate, well, your pure state can be separated into two parts equally, well, with the weight of one. So you have to be really careful about the story of counting. Here it works perfectly well. For cuts which are a bit more tricky, it's not like if you don't have a single state, it's not a product state. Being a product state depends a little bit on the basis that you want to consider. But we will discuss this point later in the lectures.
So in this sense, it makes sense to cut my system in half, because then I have the maximum number of labels that I can label my levels with, my entanglement spectrum levels with. Because if I cut, for example, if I have a huge chain and I cut only one side and consider it to be A, I have only two labels. For all
Right.
For all the
Okay, so now I want to give you some brief summary of the entanglement entropy. Well, the question is the following. How can we quantify entanglement in a system? There are many ways to do that. You have many ways to give some number, just to say, oh, entangle are two parts of your system. Maybe the most natural one is the Feynman. entanglement entropy. So the entanglement entropy, or the Feynman entanglement entropy, is just minus trace of A of the reduced density matrix A times the log of rho A. So if you have done the calculation of the Schmidt decomposition, or if you have diagonalized the reduced density matrix, of course, computing the entropy is quite trivial because you have all the spectrum, so we'll be just psi I exponential of psi I. You can compute the entropy for the B part of your system. It's the same story. And once again, by the argument that the two spectra, the one of rho A and the one of rho B, are identical, at least for they all have the same non-zero eigenvalues, then you get it's also some I, psi I, exponential psi I, so it's equal to S. And of course, a property is that here there is no reason for when you take the sum of the entropy of A and the sum of the entropy of B to get the sum of the entropy of A plus B. If it's a pure state, the entropy of S A plus B is just 0. In the generic case, we don't have that SA plus SB is equal to SA plus B. So, how people use the entanglement entropy to probe topological phases. So, from a practical point of view, let's say you want to characterize a system using this kind of tool. The first question you should ask, and I think that's true for when you do any numerical calculation, when you do simulation, is the result that I will get by computing this much better than a random output? So it's always useful to compare what you get from a random state, and you compute the entanglement entropy, and let's say a topological phase. Because of course, when you have numerics, if you're doing some finite size calculation, it would be very difficult to extract something meaningful. So it's always a good thing to compare with a random output. So if you take a random state, and I will also assume the following properties, that dimension, the subspace B is greater or equal to the one of A, and it's much bigger than 1. So if you have this property, you can show that the entanglement entropy will go like log of the dimension of A, and there's a correction, this, which is dimension of A divided by 2 times dimension of B. So that's the average entanglement entropy that you will get from your computer. If you just use, if you ask to a monkey to give you like wave functions and you average over all the results, this is what you will get. So of course, in a situation where actually dimension of A is much smaller than the dimension of B, this will just give you log of dimension of A. So once again, we can go back to the example of a spin 1/2 system. If you take spin 1/2 system, basically the dimension of A will be the number of spin that you have in A. So as an example, so VS spin 1/2 in A. So the dimension of A will be 2 to the power VA. So the average entanglement entropy will be VA times log of 2, or the average one. So,
is it a self-averaging quantity in the sense that suppose we fix a dimension of A and we let dimension B grow, does the mean square deviation, for instance, go to 0, a little bit like in a central limit theorem? Because sometimes it's very hard to generate a random state, so its result, I guess, is useful if it doesn't fluctuate too much from one state to another. If you want to... because you want to compare the ground state to a random state, so you're going to compare what you find for the ground state with this value, but suppose this distribution is very broad. You could be simply unlucky somehow and choose
short answer, I don't know. So let's say... my guess is, well... I mean, this the proof for this result. I don't know the assumption about exactly what the...
no, but I think the result is correct. But
no,
you could be unlucky in the sense that you could find, for instance, a ground state that has a very low entropy, so you would say fine, but it could be that if this quantity fluctuates a lot, the state that has a low entropy may not be the ground state, but if the distribution is broad, you cannot...
All story of comparing with the random output. So the thing I would like to point out here is that the random, the average entanglement entropy for if you take random states goes like the volume of your system A. Right? So that's why it's quite abstract when you write it like this as a dimension, but now imagine you have spin 1/2. Basically what you see is that it's linear with the number of spin. Which is, do you have a volume law? That's my...
Okay,
And now, when you look at gap system, the story is quite different. For a gap system, you will get an area law. So, for 1D gap system, you can show that the entanglement entropy is bounded by a constant. Now, if you move to higher dimension, and you still consider a gap system, then you will see that the entropy is so that's the, if you're in 2D, that's the perimeter of the boundary between A and B. So let's imagine I have my full system here. I cut a small piece A. The perimeter between A and B has a length L. The entropy will be, that's a constant, which is non-universal. We'll come to that point later for when we discuss the topological term. And so, contrary to the random case, where you have volume law, here you've got an area law. It only depends on the area between the part A and the part B of your system.
So this is for all kinds of gap systems, not for...
This one is proved by Hastings. I think this one is just conjecture for higher dimension.
No, but I mean that the reason why it's gapped doesn't have to do with whether it's topological or not. It could be ordered.
Finite correlation length in your system. Right? The intuitive picture is that if you have finite correlation length in your system, basically all that matter here will be what's going on around the boundary between A and B.
Okay.
Right? So you can imagine that encoded here you have the correlation length of your system. So somehow it's like a volume law, but only on this volume with like a finite thickness and not the full A.
The argument seems quite solid, so why is it not true? Or what makes it hard?
Good question, I don't know.
I mean, it
even
would be that you could have a fractal boundary, no? In this case, it would be kind of difficult to estimate what the perimeter is.
right.
The boundary cannot be...
I think we have to be careful about this area. I mean, I think when you have example corners in your... You can have like some subtle correction, so, yeah.
You define the volume by basically looking at the dimension of A and writing this to the power volume. So can you also define the area in that somehow in the same way?
Well, that's what I was pointing out. Imagine the gap system, you have finite correlation now, right? So basically it means that the part of A that will interact with B, that will be integral with B, that will be the part of A or the part of B which is in a region of thickness roughly like a few times the correlation length of your system. Right? So now, I mean, how much volume you have? It's the correlation length times the perimeter between A and B. So that's why the correlation length is a constant. I plug that into this number here, and I still have the perimeter. So when I will change the perimeter, of course you have to assume here that the area is for a 2D system is much bigger than the correlation length of your system. Yep.
So for what system did you write the volume law? That's for what system?
That's a random state, right? Take random states, compute the average entanglement entropy.
In any system, whether it's 1D or higher dimension or
Yeah.
gap.
Yeah. You see, that's a result that only depends on that kind of decomposition here.
Okay, but then this area law, this is for the ground state?
This is for the ground state of gap system. Well, actually, it's been... let's say for our purpose, we will consider only the ground state of the system. Actually, if you look at excited state of such a system, you also have the same area law.
And also, you said volume and area. There it's like the volume in VA. Is that referring to the Hilbert space and the dimension?
Yeah, VA is the number of spin 1/2.
Is that the same as this? I mean, is this an area, like an area in a Hilbert space? I mean, it seems like a different volume.
I think my point was just to give you some insights or some idea why you have a volume law if you have a random state, right? This kind of statement, I think you can understand. If you assume this formula, which is basically just some result coming from random matrices, the physical picture of how you understand this formulation here is to assume that your system is made of like a lattice, for example. So my point is to say that the dimension of the Hilbert space, but for the part A, is basically related to the number of sites or the number of spins that you have in your system. And the Hilbert space is always exponential with the number of sites. Right, so that's why you have an area.
And with the area law, what if I cut my system in momentum space or some crazy coordinate?
Can we talk about that next lecture? Yeah, I will. Don't worry, I will address this point. I would like to finish today with the case of topological phases in 2 dimensions.
You have a question.
Again?
Yeah, sorry. I'll buy you some car.
That's so great.
So, could I use the entanglement entropy to see if a finite system is gapped or not? Because sometimes in finite systems the notion of gap or gaplessness is a bit iffy because you increase your system size and then you see that your gap closes. For example, magnets. Could I use perhaps the entanglement entropy to say that even though my finite system seems to be gapped, actually it isn't?
Well, we go back to the original question. Basically, a gap is a notion you related to the Hamiltonian of your system. So now here you're just computing a property of the ground state.
Okay.
I can always build the worst case. Take a state which is just a product state.
Yes.
Right. So this one, the entropy will be 0. So you can say, well, that's the area law with just a constant equal to 0. Okay, but now on top of this one, I can always build any kind of excitation that I want, and I can make the system gapless without any trouble. So that's why in finite size system, it sounds to me very difficult to go the other way around, like to claim if I satisfy the area law, then without additional assumption about your system. Okay, so in 1 minute, let's have to look at the correction. So for 2D topological phases, so they are gap system, so they satisfy the area law, but the interesting point is not the area law. I mean, if you have to check numerically if this is topological phase by this technique, first, be sure that this is an area law and not a volume law. And then you have to look at the first correction, which was shown to be a constant. That is related to the properties of your topological phase. So dA is the quantum dimension of the topological sector. A, so which means like the kind of excitation, one type of excitation in your system. Capital D is the total quantum dimension. Basically, don't worry too much about this. This is just a way to say that when you have topological phases with let's say abelian or abelian excitation, and you add more and more excitation into your system, you know that you will generate more and more wave functions, and more states. So this quantum dimension tells you exactly how the Hilbert space for a given type of excitation will grow when you add more and more excitation to your system. So it's a characteristic. It's a way. It's a way to characterize your excitation of your topological phases. These numbers. So that's why if you can extract the first correction to the area law for topological phases, you have an indication about the nature of the excitation of your system. So, of course, the end of the story here is that if you want, once again, to do that numerically, it's actually quite non-trivial to check that you have the area law and to extract the constant, the topological entanglement entropy. If you have a DMRG, sometimes it works pretty well. For excitation, you'll almost always killed by the finite size system. So what we will discuss during the next lecture is the entanglement spectrum, and I will show you that even in finite size, you can still get lots of information there, and especially about the excitation. Okay, thank you. Coffee break? If you have questions, you feel free to ask me as much as you want after the lecture.
Can I buy you the coffee here?